Okay, so today what we're doing is we are going to find the volume of certain objects, and the way that these objects are created is that we are taking a region underneath the curve. So basically what we're going to do is we're going to take a region.
3D.
We're going 3D. So basically, we're going to take a region. Let's pretend that we had this region here. And we're going to rotate that around an axis of revolution. Now, we could have a variety of places that we could rotate it. But let's suppose that I were to rotate it right around this point here. When I rotate this around, it creates a 3D object. What this would create is something that looks a little bit like this. And it's basically kind of like a bowl, if you would, or a cone with a little bit of solid there. So what we're going to be doing is taking these regions, rotating them, and creating a 3D solid shape for it. Obviously, depending upon your region and how you rotate it is going to determine what the shape looks like. Obviously, this rotate around is going to look different than that. So to help us in visualizing this, let's go with the super easy one, a triangle. If I were to take this triangle, and let's just rotate it around our x-axis here. When I rotate that around, we basically have a cone. And this would be a solid cone because this is all solid here and solid right. So we would have that solid cone shape. Now, what if I were to rotate it around my y-axis? We would still have a cone. It would be a little bit of a different looking cone. It would be taller and a little skinnier. But you can see that this would change our shape if we were to take it and rotate it, let's say, around this line here. We would take this solid and rotate it around this line. We're going to now have that gap within it. So we have kind of a cone funnel shape. Okay, so this is what we're going to be doing, and I love this topic in Cactus because I feel like you've been doing all this math all along, and here's something that is a little more tangible. And you're like, oh, you can use Calculus to find the volumes for this. So this is what we're going to be doing today and next class. I think we're going to just do disk method today, and then we'll save our wash method for next time. So our disk method is where we don't have a gap. Our wash method, what we'll do next time, is that we do have a gap when we do make it. So first I want to kind of illustrate to you what's going to be happening in this. Geometry Sketchpad is someone who created this, which is super great, to help us kind of see what's going on. I'm going to take this here. Okay, so basically what we're doing is, again, we're taking this region and we're rotating it around. And we know that that area underneath the curve we can find by using our integral. And we know that another way of finding our areas are basically those little rectangles. So the integral is basically taking infinite little rectangles and adding those together. So that's why you'll see this rectangle here. I want to move my axis of revolution. Let's go right here. Okay. I think I want to go ahead. So if we take just that shape there. I know this is so they're just taking one chunk, one little rectangle for it, and they went ahead and then chunked it up into multiple rectangles. Now, what we're going to be doing is, this is obviously just taking the rectangles and stacking them. We're going to actually do the smooth curve, and I think our next one gives us that. Okay, so here's the same region. We're going to actually be finding the exact shape there, so instead of chunking it into rectangle, we're finding an actual shape. So let me go ahead and so you can see it makes that 3D shape there. Here it's kind of like a tree stump that's been curved, if you will. So as you can see, as we move along, our discs, if you would, so basically the idea is that if we were to slice this, our discs are going to be those circles. Our circles have a radius that's just the height of our function. So what we're actually going to be doing is integrating our area formula for a circle. What is the area formula for a circle? Pi r squared. And our radius, I'm going to pretend that I only heard pi r squared. Our radius ends up being determined by the height of our function. Okay, so let's take a look at another region. What else? So we can have, again, instead of rotating around the x-axis, we could also rotate around the y-axis. We can have that's rotated around just a horizontal line. Let me reset this so you can kind of see. If I were to change my axis of revolution, we should expect to see a gap here now. So you can see that's going to change our shape for it.
Can you rotate it again?
What's that?
Like, can you do it across the y-axis again?
Yeah. Hold on. Let me. While it's 3D, I don't think it lets me do that. Okay, and then again, we can see that it's going to change our shape if we were to go above. Let's put our axis revolution right there. We can expect that it's going to make that cylinder with kind of that funnel shape cut out of it. Okay, I want you to evolve. So now our shape is different because our axis of revolution is different. So we're finding then a different volume here. Okay. Now we should have. Okay. I think, does this one let me go around the Y? Okay. So here's another example. This one's going around the Y-axis. We're still going to be integrating. You can see that all of our little chunks are still circles. This would be an example, though, of where we have that gap, and we'll have to subtract that out. So that'll be next time. Let me put this back on. Okay. And so once again, you can see how it changes. Now, one thing that we do not deal with in Calculus AB is they will never put your axis of revolution in the middle of the object. You can still find that region. It's obviously going to look a little different. But we don't do that in AB, so don't worry about that. Linear algebra is actually matrices. But I don't know if they do it in BC or multi-multis when you start bringing in the z-axis. So I'm not sure. I don't think they do that. Oh, yeah. Yeah, so you guys thought Calc AB was hard. Multi's a lot crazier. So multivariable calculus AB and BC is single variable calculus. We only do it with respect to x or respect to y. Multivariable calculus, you're going to go dx, dy, dz, or variation of it. So they bring in the z-axis and they have 3D shapes. It's really cool what all you do with it. Yes, Gary?
Why don't they give us a 3D shape finding it after conversion?
I mean, the 3D shape is determined by your function. So we're going to be using our function to find that volume. Rather than just saying, here's the 3D shape, you'd have to find infinite radiuses to find all the different circles. We're going to be using the function to find all of our radiuses for us to find the shape. It's not like it's just a cylinder where it has the same radius the whole time like you had back in geometry.
Wait, are we finding the volume of the 3D shape or
yes.
Like right now?
This is a 2D flat surface. So the volume of the 3D shape getting rotated around, which is based upon our region, based upon our region.
Okay.
So this is what we're going to be working with today in next class. Again, we're going to stick with just the, okay, I want just a normal one. We're going to be sticking with just disk method, which is when we don't have a gap. So going back to this one. Okay. So what we're focusing on today are these ones here. Now, it's not always going to be revolved around your x-axis. It might be that your region is up higher and it gets revolved around something higher, but we're going to be dealing with today where we don't have a gap. It's that solid shape, no gap. Okay. So that's what you see happening in your notes there. Let's just go ahead and take a look at what we've got for today. Okay, so here's a lot that you can read, but I trust you can read on your own sometime. So the idea that we have is we have this region underneath our curve. Use a highlighter actually. We're taking this region, and this region's what's getting rotated. And so as we said, if we were to slice this, our cross sections would be circles. And so what we actually want to do is we want to integrate our area of the cross section. And if you would, go ahead and write that at the top of your paper there. Volume equals the integral of the area of the cross section. Because we're actually going to be coming back to this again next class, the class after that. So volume is the integral of the area of your cross-section. Before, when we were doing integrals, we were essentially adding together all those little rectangles. So now volume, we're adding together all these little circles. And so our area of the circle would be the pi r squared. So your volume is always the integral of the area of the cross-section. It's just when we're rotating around a line, our cross-sections end up being circles, which is why we're integrating pi r squared. Now, again, this could be with respect to x or with respect to y. You might see this notation, WRT with respect to x, WRT with respect to y. That's all it means. They will tell you what they want. Okay, so they'll either say with respect to x, or they will give you a horizontal axis of revolution, which means you have to go with respect to x. Okay, so let's just write that out. So this is going to be a horizontal axis of revolution. And axis of revolution is just the line that we're revolving around. If we have a vertical axis of revolution, that's when we're going with respect to y. Okay. So your radius should always be perpendicular to your axis of revolution. Here we're rotating around the line y equals 0. So my radius will be perpendicular to that. So my radius of the circle is really just going to be that height of our function there. So we're looking, basically we're going from the center of our 3D shape to the edge, which will basically be from the bottom of our region to the top. Okay. So the key thing is always to draw a picture, and it's really important that you know your paragraphs to get an idea of what's going on. So we still have to do kind of sketch our graphs, find those intersection points just like we had to do with our area between the two curves. It's just now we're taking that area, and we're still going to be integrating it, but we're going to integrate it where we have pi r squared. So honestly, the biggest mistake that students make with this is forgetting their pi. The second biggest mistake is forgetting the square. Sorry. Okay. So our first one, find the volume of the solid formed by revolving the region bounded by y equals 2x, y equals 0, x equals 3, and x equals 0. So let's just go ahead and do a little sketch of that. Your sketches do not have to be super fancy. They're just there to kind of help you identify what your radius is. Alright, so volume solid formed by y equals 2x. And again, just a rough sketch is good. So let's see, that's going to intersect at 0, 0. So 2 over 1. We're going from what, 0 to 3? Maybe I should made mine a little taller. That's all right. 1. Never spend this long drawing a picture. Get back to 1. Alright, so we've got our approximate figure here. Y equals 2x, y equals 0, and x equal to 3, and x equal to 0. Okay, so we've got this region here. And we're going to take this region, and it says that we are rotating it around the x-axis. Alright, so I like to just use the dotted line to indicate my axis of revolution, and I like to draw just a little arrow indicating that I'm going around the x-axis. So my radius, always from our axis of revolution to the edge of my shape. This is going to be my radius here. From my axis of revolution to the edge of my shape. As you can see, my radius changes based upon where I am within my solid here. Now, it's totally up to you if you want to go ahead and draw your 3D shape. I personally like to go ahead and draw a 3D shape just to kind of get an idea of what's going on. I just reflect the area down there and kind of just do a circle. So that allows me to see it's basically a solid point there. But the key thing is to identify what your radius is. So my radius, I'm just going to write it out, is, again, my top function minus bottom. Now my top function was just 2x, so it's turned by the height 2x. My bottom function is just 0. So I could do 2x minus 0, or it's really just the height of our function 2x. Okay. So my integral then, I want to integrate. Where am I going to integrate from? What are my bounds? What's my starting point of my object? At 0. Where does my object stop? At x equal to 3. Okay. Notice I'm going around a horizontal axis of revolution. So I'm going to be going with respect to x. My equation should be in terms of x. So I'm going to just write with respect to x over here. So horizontal axis of revolution, my radius is perpendicular to it. My radius, so again, we want to integrate pi r squared. I'm going to go and label this volume equals pi r squared, and my radius is 2x. I like to go and set up where I just put parentheses squared, so I'm less likely to forget that squared component. And make sure you do have parentheses because it's not 2x squared, but rather the quantity 2x. Okay, so these were actually just our limits. That's all of that for concern. Otherwise, we wouldn't know where we would be stopping. Okay, so let's go ahead and integrate this. Let's see, so we've got integral from 0 to 3 of 4x squared dx. Don't lose your pi all the way along. So we'd have 4x cubed divided by 3, evaluated from 0 to 3. Go ahead and take in 3 and put it in. So we've got pi times 4, 3 cubed over 3 minus pi times 4 times 0 cubed over 3. That's just going to be 0, so our answer would be, let's see, 36 pi. Let's see, 3 cubed, we can knock off one of those 3, so it's really just 3 squared is 9 times 4 is 36 times 5. Yes. Again, for response, guys, you do not need to simplify. Please do not simplify. Stop right here. And they do like these types of questions for free response. And ideally, in 2 classes, we'll go take a look at some of the free response questions in the GPs. That what they like to do is first have you find the area between the curves, find the volume rotated. Sometimes they have the volume with cross sections, and they usually have the property with it. Yes.
So why are we integrating just the radius?
So what we're integrating is our area of the cross section that gives us our volume. Our cross section, when we split this, if I were to take a butter knife and slice this down, I would get circles, right? I get discs. So our cross section is a circle. We're integrating the area of a circle. The area formula for a circle is pi r squared. So what we're doing is we're integrating that, but our pi is a constant, so we just bring it out. And then our radius squared, the radius is based upon our function there. So what this does is this is taking the radius at every little point, finding that area of that circle, and then adding all those together is essentially what's happening. Yes?
So we got radius just by subtracting 2 functions, right?
Yes, and so right now it seems silly for me to say top minus bottom, but it's important for our washer method when we start having that gap, so I'm going to just kind of rehearse that now, but obviously our bottom function is 0. Yes,
Are
Gary?
we given a formula sheet for class?
Ooh, that's a good question. You are not. Now, sometimes they will give you, like within, at the start of the problem, or sometimes within the problem, they might give you like volume of a sphere or volume of a cylinder, but it's never guaranteed. So you should be familiar with this. So volume and surface area of spheres, cylinders, foams are probably the most I've ever do. But in recent years, I've seen them give those formulas to you.
So I don't understand why we don't just find the volume and see if we can find the free shape. Why do we have to go through the full integration?
Well, how would you find your volume of this stuff?
I mean, I don't know the formula.
You mean just formula for a cone? So for this one, it's nice because it's a triangle, right? But let's suppose that I had a parabola and we took, let's say, this region here. And then rotate, like, so actually, let's not take the whole region, let's just take this part here and rotate it around. So we have that bowl. Do you know the formula for finding the volume of a bowl? I don't either. It's not half of a sphere. It's going to be different based upon how like skinny or wide it is. So this allows us to find the volume irregardless of the shape. This one, yeah, we have volume for a cone. So for this one, we could use just the volume for a cone. But once we start having any other type of shapes that's not those standard shapes, then we don't have a formula for it. And then also too, once we start removing like area from it, then we start having issues. So this allows us to find that volume regardless of what our beginning shape is. But you're correct, this is a cone. We have volume for a cone. This is a right cone, and it's not a slanted cone, so we could use the volume formula for a cone for this specific one.
So if it's a known shape, then we don't have to go through the whole process.
Sure. But I'm betting that they would probably say using integration or something like that. They probably have some type of, or most likely they're probably just wouldn't give you one that was nice. They probably give you this. But you're correct. For this shape, we would be able to just use the area or the volume. Okay. So again, it goes back to integrate your area of the cross section. Our cross sections are circles, so we're integrating pi r squared. Okay, let's take a look at. As you can see, there are a bunch of different problems in here. There's endless options as to what kind of shapes you can have. I want to go ahead and take a look at, not this one, I think that's a different one. This is a little more exciting. Let's go to number 3. So find the volume of the solid formed by revolving the region bounded by y equals x squared. Y equals 0, x equals 2, and x equals 0. Okay, so we've got a parabola. Bless you. And I have y equals 0, so that's just bounded by the x-axis here, or yeah, x-axis here. X equals 2, and x equals 0. All right, so what we have then, the region that we are rotating, bounded by our parabola, our y equals 0, x equals 2, and x equals 0 is just this little region here. And it says around the x-axis. So once again, I'm taking this region here, and only this region, not over here, because they said x equals 0 and x equals 2. So I'm making this region, and I'm rotating around the x-axis. Again, a horizontal axis revolution, so I'm going with respect to x. So again, to determine my radius, I want to go from my axis of revolution to the edge. So my radius, so the top function, which would be x squared, minus my bottom function, which is 0, so x squared minus 0, which is x squared. So we want to find our volume. Volume equals pi integral r squared. My radius is x squared. And we are going from 0 to, what did they say, to 2. Okay. So let's go and integrate. Let's see. We've got from 0 to 2 of x to the 4th dx. Notice again, it's with respect to x, horizontal, with respect to x. So I'm doing dx, my functions in terms of x, my bounds are in terms of x. Alright, so pi x to the 5th divided by 5, evaluated from 0 to 2. So it'll be, what's 2 to the 5th? Is that 32? Yeah. So 32 pi over 5 minus 0, so just 32 divided by 5. Questions with that?
Yeah, I understood like that we were integrating the area formula for a circle, but now it's not integrate the circle.
When we do, so when we look at our shape, I'm glad you said because I forgot to draw the other part of my shape. It's not a, our curves, we have curves here, but when we do our cross sections, when I take slices, our slices are still going to be little discs. Does that make sense? So you're correct, like it's curved, but our slices are still discs. Does it feel overly warm to you guys? Oh, okay, I'll leave it alone. Other questions with this? Okay. So as you can see, it's not always just a nice parabola or line. We do bring in other graphs like square to sine x. We could have natural logs and exponentials. I want to take a look at one where we're not going around the x-axis. So let's go, I think number 5 I want. Yeah, let's do number 5. So find the volume of the solid formed by revolving the region bounded by that, and 1 around the line at y equals 1. So I've got 2 minus x squared. I personally like to write it like this. I have an easier time recognizing what's happening. So I have a parabola that's been flipped upside down and shifted up too. And I'm going to just label this as f of x. Since they called it f of x, I'm going to use f of x. All right, and it says bounded by that in y equal 1. So we're looking at the region bounded by those two curves. We're looking at this little guy here. I really should be drawing the pictures bigger. Okay, and it says to rotate around the line y equal to 1. So we're rotating around this line. This is my axis of revolution. So I, again, have a horizontal axis of revolution. That's going to be with respect to x. So I know I'm doing dx function in terms of x, bounds of x. So this can be kind of a funny looking shape. But my radius is determined, axis of revolution to the edge there. Okay, so here's my radius. So now our radius, when we do top function minus bottom, my top function is my f of x function, minus my bottom function would be g of x. Or we can just actually write out what those functions are. So it would be x2 minus x squared, or negative x squared plus 2, either way. 2 minus x squared minus 1. Now I'm going to go ahead and simplify this before I throw it in my integral. But I have negative x squared plus 1, so 1 minus x squared. So this is going to be my radius here. Alright, so again, my radius from my axis of revolution to the top. And it's top function minus bottom. So here you can see our bottom function finally made an impact because it wasn't just around our x-axis. So we're still rotating around there. I'm just going to go ahead and kind of complete that shape. So I just reflect it. And so you can see, once again, as we slice it, we're still going to have those circles. I don't know what kind of shape that would be. Makes me think of a tortoise on top and the bottom. But, okay. So this is our radius. So once again, we have our volume equals I r squared. So we're with respect to x. So our radius we said was 1 minus x squared. Again, on AP, you could leave it unsimplified. You could even say f of x minus g of x quantity squared. Just want to make sure you have that parentheses squared is a huge thing. Sometimes people like to do it like instead of brackets where they'll put this in it. Totally up to you. I just like to have this simplified so I don't lose any pieces of it. Okay, so the question is, what are our bounds that we're going to? How do we figure out what we're integrating from what x costs? Yeah, it's those intersection points, so set them equal to each other. Just like we had to do with our area between the two curves. Okay, what were our functions? 2 minus x squared, I remember here. 2 minus x squared equals 1. Express x squared equals 1. Is x equals plus or minus 1? Is that right? Sweet. And then now we'll integrate. Do make sure that you are careful when you integrate. We have to square this. We can't just do reverse power rule and say this is the third power divided by 3. This is a function inside a function. Do we need u sub? No, let's not do u sub. Let's just go ahead and FOIL this out. So we have then volume equals pi, negative 1 to 1. So let's see, we get 1 minus 2x squared plus x to the 4 dx. Let's make sure we got that right. Okay, so now let's go ahead and integrate that. So again, the setup is really our only new thing. Now it's just the integration that we've been doing for half a year now. So we've got, I'm going to leave my pi in front. So I've got x minus 2x cubed over 3 plus x to the 5th over 5. Now we're taking towards 1. I'm going to borrow my space here. You can leave your pi out in front of all of it, or bring it in. I'm going to leave it out in front of all of it. So I have 1 minus 2/3 plus 1/5. Parentheses minus, parentheses, don't, like, be liberal with your parentheses. Why not? Make those AP readers sick, they're all good. -1 minus 2 -1 cubed over 3 plus -1 to the 5th over 5. You guys, if it's a free response, you can stop right here. No need to simplify all those negatives. If you do simplify it, it comes out to 16 pi over 15. So once again, it's the same idea. We don't have a gap. It's just our x revolution is meeting where we are, so we just take that consideration for our radius. Okay, any questions about that? All right. So we're going to take a look at number 9. So this is kind of going back to our beginning graph. So we have y equals 2x. Y equals 0, x equals 3, and x equals 0. Okay, so we've got this region here, but now we're rotated around x equal to 3. So now we're rotating around x equal to 3. That's a vertical axis of revolution. Okay, so now we're going with respect to y. A vertical axis of revolution with respect to y. And so my radius, instead of going, so we have to still go from our axis of revolution to the edge, but now our axis of revolution is a vertical line, not a horizontal line. So I'm going to go from my axis of revolution to the edge. Here's my radius. So since we're doing a vertical axis revolution, everything has to be with respect to y, which means when we integrate, we're going to have to integrate not 2x, but rather y over 2. Okay, so once you recognize that we're going around a vertical axis revolution, let's go ahead and change everything to be in terms of y. So I'm going to rewrite this. I'm going to solve for x here. So I get y over 2 equals x. So that's the function I'm going to be using to actually rewrite this. X equals y over 2. Okay. So now when we go to do our radius, before we did top minus bottom, now we have to do right minus left. Okay, so remember with y we go right minus left, x we go top minus bottom. And you can just turn your head and then top minus bottom. So my radius, I'm going to go right minus left. So my right function is going to be x equal to 3. That's what we have here. So my right function would be 3. My left function is going to be this actual function here, y minus 2. Okay, so same idea. If I return my head, top minus bottom, but we're just going right minus left. So everything else is the same. Our volume is pi integrate r squared. Now we're going to y. Our function should have y's with respect to y, and our bounds need to be y's. So my radius, we can see we have that y there. 3 minus y over 2. Now my bounds, you gotta be careful with that. We're going with our y values. So I'm not going 0 to 3. Rather, I'm going from 0, starting here, going up to this spot here. What is my y value there? What was it? 6. How do we know that it's 6? We just put into our function here. Take 3, put it in, we get y is 6. Okay, so again, when we are in terms of y, respect to y, terms of y, balance need to be in terms of y. Just double check that I've got. Okay. So at this point, you could FOIL this out. We actually could do a little mini u sub here, because our derivative of this would just be -1/2. So you could go either way with it. Let's try the little mini u sub. Let's put in a u sub every now and then. So let's let u equal 3 minus 1/2 y. Du equals -1/2 dy. I don't have that -1/2, so I'm going to multiply that over, so I get -2 du equals dy. And we do need to change our bounds. Was it worth it to change the bounds? Maybe. Okay, so I'm going to do u of, u of 6, and I need 0. Oh, it's actually not too bad. So we have 3 minus 1/2 of 6. What? We get 0 for that one? I'm going to take 0, put in 3 minus 0. Oh, how weird is that? Okay. So I'm going to go and change it to be in terms of u. So I still have that pi. My bounds need to be in terms of u, so instead of 0 to 6, we're going 3 to 0. This becomes u, and dy we said was -2. I'm going to throw that in front. Di. So now it's actually not too bad. I don't know, I feel like that'd be better than foiling it out and dealing with the fractions. I don't know, maybe it's 61 back to that. It's not too bad. Okay. So do my inside derivative of -2 pi u cubed divided by 3, evaluated from 3 to 0. We could go ahead and flip our bounds and negate it so it's positive, but we can just leave it as is and evaluate it. So I get -2 pi. Oh, we take 0, put it at 0. So I just get 0 minus, and then I take my 3, put it in. So -2 pi, 3 cubed over 3 becomes positive. 3 cubed, 3 squared. Is that 18 pi over 3?
Yep.
Sweet.
No,
Oh no, it's 18 pi, right? We got rid of that 3 in the bottom. Just 18 pi. That actually wasn't too bad. We avoided all those fractions. Okay, so again, you could have FOILed this out, but doing that little mini u sub got rid of our fractions for us. That other one, where's our other one where I said not to do the u sub? This guy, if I were to try to do a u sub here, my derivative, this would be -2x. There's no x to cancel. That's why we couldn't do the u sub there. Here, my u sub, when I do my derivative, the inside, it's just a coefficient, so that's why I did this first. Okay, so when we have it with respect to y, it's again the same concept. We're still integrating pi r squared. It's just you have to make sure your equation. Bless you. Here, you were on it right there.
I saw it coming.
So you just need to make sure you change your equation to be in terms of y. Change your bounds to be in terms of y, and when we figure out a radius, we're going right minus it. Questions with that? Let's go ahead and set up another vertical one. Let's see. Is there anything more exciting than just use the next squares? Let's go number 15. So again, guys, there's a plethora, there's like a never-ending list of volumes you can do by rotation. So these other ones are just extra practice sheet dues. I've got homework sheet for you. Okay, number 15. Find the volume of the solid obtained by rotating the region bounded by this guy. Sweet, something exciting here. A little square root going on. So 1 plus the square root of x, so that shifts it up 1. And then also y equal to 1 and x equal to 4. Okay, so we are looking at this little region here. And it says that we are rotating around x equal to 4. Okay. So we're going with respect to y, because it's a vertical axis revolution. So my radius, when I determine it, remember, should be perpendicular. Always go from your axis to the edge. Here's my arc. So everything's going to be with respect to y. So I guess we have to solve for this in terms of y. Let's rewrite this guy here. Let's see, we've got y minus 1 equals square root of x. Square both sides.
4.
We really only have the top part of that, though, don't we? Okay. So our function is y minus 1 quantity squared. We only got that top part of it. That's fine. I'm gonna write that here. Okay. So now when we get to establish our radius, again we want to go right minus left. Right was x. So right minus left, and left is my function, which is this guy here, y minus 1 quantity squared. A little bit crazy of a radius. I mean, still not too crazy. Okay, so we could go and set up our volume integral at this point, or we can simplify and then set it up. If you have a calculator, don't waste the time of multiplying this all out. Just go ahead and set it up. If it's not calculator, though, it's probably going to be in your best interest to simplify this. So we've got 4 minus, make sure you still have your parentheses in it. See, we've got y squared minus 2y plus 1. So it would be negative y squared plus 2y plus 3. Okay. And then we'll just go ahead and set it up. So my volume equals I integral a radius squared. I'm going with respect to y. So negative y squared plus 2y plus 3. And we want our y bounds. We're starting at 1 and finishing at where they intersect. And I'll tell you that that occurs at 3. But we would once again just take 4 and plug it in there. Oh, no, y squared 4. Okay, so then we integrate that. So, again, same idea for y, it's just we go right minus left. Questions with that? So your homework is going to be this volume by discs worksheet. Really, I'm going to throw yours in this row so that you can
Is this murder?
Yes.
If it's multiple choice, could it you just, like, you could just choose its own plus one? And the answer was close to what you'd actually get.
Possibly, although you would be losing a good amount of, like, depending on how wide that is, you could be losing a good amount of area. So that's, I mean, if you're in a crunch, you could try that, you know?
Those were the days.
So you can definitely try that. I wonder if they would put them in the reviews. I don't know. Like, they might just give it as one of the multiple choice. But you would know then not to choose it. Could be. It would kind of depend. Do you get to pick one? Sorry, I will take that. Okay, so again, your homework is volume by discs. Up on Blackboard are other notes with discs if you want extra practice, but this is your homework.